In this video we will go over calculating the pH of the weak acid acetic acid, and then we will also calculate the pH of the exact same solution in the presence of its conjugate base. So anytime you see the acid, this one is called acetic acid, the conjugate base, sodium acetate, actually is the acetate ion, again, the conjugate base. The sodium ion is just a counter ion, also known as a spectator ion. It does not participate in any of the reactions. So part A is just a simple ice table. Part B is when you add the acid with the conjugate base, you get what's called a buffer. One thing I want to emphasize is do not worry about the sodium. Sodium acetate is the acetate ion and sodium ion separately in water. But anytime you have the combination of the acid and conjugate base, we call that a buffer. So part A is just a simple ice table that we've been doing so far in the class. So let's go ahead and solve for part A. And then with part B, it's very simple. What we will use in part B is called the Henderson-Hasselbalch equation. That Henderson-Hasselbalch equation is the best way to find a pH of a buffer solution. So first off, anytime we do these types of problems, we have to write the equation. And the equation for Ka, which is, in this case, acetic acid, the acid will react with water. This is a weak acid. It's not a strong acid. A strong acid is one of our six. Weak acids will deliver a proton, though not as strong as the strong acids, and they will give you the conjugate acetate ion, and then all Kas will react with water, and all Ka reactions will give you H+, also known as the hydromonium ion, but I use H3O plus and H plus interchangeably. So the question here is we start off with 0.4 moles per liter is our concentration. It's a weak acid, so this is the best example of an ice table. So 0.4 is our starting, and then we have 0 and 0. Some of this reaction is going to go this way, and how much is that is minus x, and plus x and plus x. You see the weak acid is going to ionize and deliver protons in the form of H+, but we don't know what extent because it's a weak acid. If it was a strong acid, the arrow here going in this direction producing H+ would be close to 100%. Because it's a weak acid, we don't know, so we're going to use our ice table, 0.40 minus x for acetic acid. The conjugate base to this conjugate acid is plus x, and it will have the same concentration, the acid, to this conjugate base. So now we have all of our final equilibrium concentrations. Remember, ice stands for initial change in equilibrium. Let's go ahead and solve this into our Ka. So this Ka constant we will have to look up in our book, or we can consult any resource. I have found this at 25 degrees. Remember, we quote this at a specific temperature. Products over reactants, each one raised to the stoichiometric coefficient. Ka I found to be 1.78 times 10 to the minus 5. Again, we look this up in our textbook or internet, any internet resource. The equilibrium concentration of acetate is x. The equilibrium concentration of H+ is x. So x times x is x squared divided by 0.4 minus x. Okay, I'm going to go ahead and use my low ionization assumption and assume that 0.4 minus x is essentially 0.4. That is to say, this ionization, the reaction going this way, is going to be so small and so insignificant that 0.4 minus x is essentially going to be 0.4. So this is called the low ionization assumption. And we assume 0.4 minus x is about, if this ionization assumption is greater than 5%, then this assumption fails, and we have to solve for x using the quadratic equation. Something we don't want to do, but we may have to do if this reaction going to the right is significant enough and strong enough. Well, we're assuming it's small enough and not significant enough because acetic acid is a weak acid. So let's go ahead and fill this new equation with our assumption. Okay, shown in blue is our low ionization assumption. Let's go ahead and solve for x here. times 1.78 times 10 to the minus 5 equals x squared. Let's go ahead and take the square root of this number to get our x. Okay, so solving for x on my calculator, I'm getting x to be a value of 0.00267 big M. Okay, so that is our x. Don't forget to put the units in our x. And that x is going to symbolize the concentration of both the acetate ion as well as the concentration of this H3O plus. So our pH is nothing more than minus the log of H plus. Okay, remember I use H plus and H3O plus synonymously or interchangeably. So pH is going to be the minus the log of our x from this ice table, and that x is 0.00267. So let me zoom in here. Minus the log of 0.00267. We don't put any units inside the log, and doing that on my calculator, I can double check my work, I'm getting an answer of 2.57. We can check our assumption if this is correct. The way we would check our assumption is we take our x, our assumption that it has to be less than 5%, so that we can avoid the quadratic equation. So the assumption test for validity is you take this x that we calculated from the ice table, okay, testing to see whether we need to use the quadratic or not. Here we did not use the quadratic. So if we're safe in not using the quadratic, we'll take this value of x, divide it by the initial concentration given to us in the problem, which is 0.40 m, and we multiply this by 100 to give us our percent ionization. The threshold is 5%. If it's greater than 5% ionization, then we have to use the quadratic. It's just too big of too strong of an acid. But if it's less than 5% ionization, less than 5% goes this way, then we are safe in our low ionization assumption. We can continue avoiding using the quadratic equation. And doing this on my calculator, I'm getting about 0.67%. Very, very well below our 5% threshold, and this is the answer to this problem. The pH here is 2.57. Now we add the conjugate base here, sodium acetate, in the concentration of 0.2 molar with our 0.40 molar. What is the corresponding pH? Once again, we have a buffer, and once again, these are the perfect complement to use the Henderson-Hasselbalch equation. So moving on to part B. Let's first write the Henderson-Hasselbalch equation. It's going to be pH is equal to pKa plus the log of, here you want to what's called drop the acid. Okay, so you drop the acid, HA, but in this case our HA is acetic acid, over A minus the conjugate. Here our A minus is the concentration of acetate ion. Remember, the sodium is a spectator ion. So we have everything we need here. pH is equal to pKa, and which is minus the log of Ka. I've looked up the Ka and found it to be 1.78 times 10 to the minus 5, plus the log of, remember, when you're figuring out this fraction, remember, drop the acid. The concentration of acetic acid, according to this problem, is 0.40 molar. I'm not going to put units inside the log. And the concentration of the sodium acetate is 0.20. Okay, the sodium is just a spectator ion. All right, so log of 1/2 plus minus the log of your Ka. And doing this on my calculator, I'm getting an answer of 4.45. So acid, you add a little bit of the base, half the base, 0.40 molar, add 0.20 molar, your pH has gone up to 4.45. This is an example of a buffer, combination of a conjugate acid and a conjugate base. We would expect buffers to resist wild fluctuations and wild changes in the pH.